Hey everybody, my name is Noah Jacobson, and today we're going to be talking about sequences. Alright, so up here we have an example of a basic sequence, pretty much as basic as it gets. Up here you have a sub n is equal to n. That's the sequence represented as a function of n. Now, the sequence itself written out looks like this. It has these fancy brackets up here, numbers, and those numbers are separated by commas. Now, an important thing to note that students often make this mistake is that a sequence is not a series. This summation thing, that is a series. A series is a sum of a sequence. The sequence itself is this list of numbers, so don't make that mistake. Now, you can take the limit of a sequence, and that limit means what is that function going to be equal to as n goes to infinity. So what is a sub n going to equal as n goes to infinity? So down here, you can see we're taking the limit as n goes to infinity of our function that we represented above, our series, and that's going to be an infinity. Obviously, if you plug this in, you get n goes to infinity. Now, a situation can occur where the limit as n goes to infinity equals 0 or some other value. For instance, look right here. You have the limit as n goes to infinity of 1 over n. Obviously, you sub in infinity there, and it goes to 0. Pretty straightforward. Now, a proof that we have to make, a theory, is that the limit as n goes to infinity of the absolute value of a sequence, if that equals 0, then the limit as n goes to infinity of the sequence just without absolute value is also going to equal 0. Now, that can be proven by the squeeze theorem. The squeeze theorem would state, as well as logic, that the negative absolute value of a sub n is going to be less than or equal to a sub n, which is going to be less than or equal to the absolute value of a sub n. Now, you can take the limit of all three sides of this equation, or inequality, I guess, and you would get 0, as shown up here. 0 is less than or equal to the limit as n goes to infinity of a sub n, which is less than or equal to 0. Now, we can tell this limit right here is going to go to 0 by the squeeze theorem. So that's a proof for this. Alright, you ready for some problems? Alright guys, for the first problem of the day, we are going to be solving this beauty. We're going to be taking the limit of the sequence as n goes to infinity. So step 1 for this should be representing this array of numbers as a function of n. So to do that, we're going to take these seemingly confusing functions that we can't really work with and mold it into a function or a sequence where we can establish a pattern. Okay? So if you just represent this stuff as exponentials, you'll get 2 to the 1/2, comma 2 to the 1/2, 2 to the 1/4. The square root of the square root of 2 is 2 to the 1/4, etc. Now you can multiply these numbers together and get exponents. As you remember from algebra 2, you can take, say 2 to the 1/2 times 2 to the 1/4 and call it 2 to the 1/2 plus 1/4, right? So that's going to equal 2 to the 3/4 and so on. So now it's time to establish a pattern. Now that we've gotten this sequence into a pretty much, it's as simple as it's going to get. Now we need to establish a pattern. So something I noticed when I isolated the exponents is that the top of these fractions are always going to equal the bottom of the fraction minus 1. See, 2 minus 1 equals 1, 4 minus 1 equals 3, and 8 minus 1 equals 7. The top, so there's our first pattern. The top equals the bottom minus 1. Now looking at the bottom alone, I see everything as multiples of 2. 2, 4, 8. That looks familiar. 2, 4, 8, 16, 32, 64. That looks familiar. That's 2 to the n, right? 2 to the 1 equals 2. 2 to the 2 equals 4. And 2 to the 3 equals 8. Great. We have a function now to represent the bottom. So now, if the top equals the bottom minus 1, the top is going to equal 2 to the n minus 1. So the exponent in total is going to be 2 to the n minus 1 over 2 to the n. And the sequence is going to be 2 to that power. Fantastic. Now we need to take the limit. The limit's going to be a lot simpler than the other stuff we went through in this problem. So let's take this function and put it into an even simpler form. So that limit is going to equal the limit of 2 to this power. Now this power we can just divide by 2 to the n. Yeah, that's going to be 2 to the 1 minus 1 over 2 to the n. Perfect. Oh, gotta do structure. There. So you're taking the limit, then goes to infinity, 2 to the 1 minus 1/2 n. Guess I'll put this in parentheses. Now, 1 to the 2n. 1 over 2 to the n. Alright, so now we just need to take the limit of this, and it's going to be 2 to the 1 minus 0, which is going to equal 2. And that's our limit. Terrific, we've solved the problem. Alright guys, for our last problem, we're going to be reviewing convergent and divergent sequences. So the question here is, does this limit converge or diverge? I'll hide the answer. So this sort of binary code-like problem, it's very hard to identify a pattern, and it's very hard to find a specific function to represent what's going on here. But what I did notice is, see, there's 1 0, then there's 2 zeros, and there's 3 zeros, all separated by a 1. So you can see down here. So there is this pattern with the zeros. However, because the function is going to alternate between two values mainly, 0 and 1, it's not going to tend to a specific value. It's either tending towards 0 or 1. So therefore we can say it diverges because it doesn't tend to one specific value. Alright guys, thanks for watching.